Previously, we had this estimate that the sum n less than x of the number of divisors of n was x log x, and then we had a lower order term 2 gamma minus 1 times x. Here gamma is the Euler-Mascheroni constant, 0.577, etc. And then the error term that we got in this previous lecture was x to the 2/3 plus epsilon. And this came from stopping at, here sigma is the real part of s, and we stopped at 1/2 plus epsilon. So essentially we did our usual Pareilles formula contour integration thing, and we stopped at 1/2 plus epsilon. And stopping here is not optimal. You can actually do a little bit better, and the idea for doing a bit better is to essentially leverage bounds on the growth of the function that we were integrating. So we were integrating the function that was the square of the Riemann zeta function times x to the s ds over s, and at 1 the growth of the Riemann zeta function squared, well, I mean, maybe I'll say 1 plus epsilon, was, I mean, saying epsilon is maybe a little bit misleading. It's actually 0, right? It's just a convergent series. You can use the triangle inequality. But let's just say epsilon because it's a little bit easier to look at this graph. So it looks like this. So this is going to be that if you look at the growth of the Riemann zeta function squared is going to be less than t to some power alpha for fixed sigma. So it's epsilon or it's 0 when the series converges absolutely, and then over here so this is when sigma equals this, and then when sigma is 0, or maybe I should say minus epsilon, you can use the functional equation and Stirling's formula, and you find that the growth of this square here is, say, 1 plus epsilon. And then over here, beyond this, this line is going to be 1 minus 2 sigma. Right, maybe, and then again, just always a plus epsilon for good luck. Again, this comes from functional equation plus Stirling's formula. So to remind you, the functional equation is that pi to the s gamma of s zeta of 2s, if you define this to be lambda of 2s, then that implies that lambda of s equals lambda of 1 minus s. So essentially these two gamma factors, right? Gamma of, you end up getting a 1 minus s over 2 over gamma of s over 2, and for each zeta factor, and this is like, the growth of this is something like t to the, it's going to be 1/2 minus sigma over 2, or sorry, over sigma. Is that right? So it's gonna grow like this when you use Stirling's formula, and you know when the real part of s is greater than 1 that the zeta function has no growth on vertical lines because, again, it's just a series. So this tells you the growth over here, and that's why when you square it, you get the square of this. And now there is this convexity bound, which is just drawing a straight line here. And this is what we used last time when we talked about this. And there's also the Lindelof hypothesis, right, which is continuing this line here all the way down to 0. And then, okay, it stays like that. And the Lindelof hypothesis, I mean, it would be very surprising if this were false. In fact, I think this may actually be known for, I mean, I think it's known that it's a consequence of the Riemann hypothesis for the Riemann zeta function. So, you should expect that this is the true behavior. And when we got this estimate, we were up here, right? By stopping at 1/2 plus epsilon, we got sort of a suboptimal bound on the growth of the square of the Riemann zeta function. Not suboptimal in the sense that we left anything on the table given the techniques that we were using and our decision to stop at 1/2 plus epsilon. But you shouldn't expect this to be the truth. But you'll notice that over here, the convexity bound and the Lindelof hypothesis coincide, right? Because over here you have just the functional equation, which is essentially totally trivial, right? So you know for sure what the growth is over here from the functional equation. It's only in the critical strip that it's mysterious. So if instead you extend over here, so instead you'll take the rectangle, something like this. And where exactly you land relative to this doesn't super matter. Then what you end up getting is that, of course, you have the same main terms, x log x plus 2 gamma minus 1 times x, and then the error term you'll end up getting is x to the 1/2 plus epsilon instead of 2/3. Right? Previously we got 2/3. If you go all the way to 0, you get 1/2. And so that's sort of a free improvement. The Dirichlet divisor problem is the question, what is the optimal error term for this estimate? And what's known about this is that I think O of x to the 1/2 with no epsilon is known. And then you can also ask, what about lower bounds on this exponent? So if you look at the divisor sum, and then you subtract off the main term, then say that this is going to be, this way. Say you have a bound of the form x to the theta plus epsilon. And you can ask what theta does this hold for. And so we know that it holds for theta is 1/2. I think there's a proof from about 100 years ago that the inf of theta, so the lowest theta you can take, is at least 1/4. So in other words, the sum of the divisor counting function minus the main term is at least x to the 1/4 in the sense of infinitely often. So some lim sup lim inf thing. And this is due to, let me check, this is due to Hardy from 1916. And this bound here, I think this is actually from Dirichlet. I don't, glancing at the Wikipedia article I have open on my other screen, I don't see exactly a reference, but I think this is due to Dirichlet. And it's probably very, very old. And what's also known is that the inf of theta, so the smallest theta you can take, is at most 131 over 416, which is about 0.3149 ... And this is apparently due to Huxley from 2003. And so that means that the smallest theta you can take is somewhere between these two numbers, this theta being sort of the best bound on the error term. And the conjecture is that the inf of theta, so the smallest theta you can actually take, is actually exactly 1/4. So it's expected that you don't, I think it's expected that, in fact, the ratio of this difference divided by x to the 1/4 has some limiting distribution. And you can find more info on the Wikipedia article.